Hello students, in last class I explained about fringe width, and today's class I will explain some more concepts on Young's double slit experiment. Alright, note. So in last class we derived fringe width, right? In that we have taken these two slits or two sources as S1 and S2, and we have kept a screen, and this is the midpoint of two slits. From that I am drawing a perpendicular line. Let us consider that point as O on the screen. Then the wave from S1 will travel at point P, and also from S2 also the wave will travel to point P. This is a S2 source. We have taken approximation in this condition to get the path difference expression. See here, what approximations we have to take means first approximation. So in the first approximation, just I mentioned x is very lesser than d. This distance is x, isn't it? This is very lesser than d, that we have taken as first approximation, right? So here remember we have to consider this is d distance between two slits, means if the d is very smaller than capital D, then we can consider the screen is at very large distance. In that time here the line from S1 and S2, that means from this point also consider one line, and from S2, these rays become nearly parallel to each other. So nearly parallel to each other means here these angles will be same. All angles we can consider it as theta. So in this diagram you observe, if you consider this angle theta, then every angle I can able to consider it as theta. So all the angles I can able to consider as theta by considering small d is very lesser than capital D. That is first approximation. In that case, what is the path difference means? In the diagram, how to get the path difference? From this point, draw a perpendicular line. So from this point to this point, this is called path difference. That is what we have calculated, S2P minus S1P. So from this point to this point, the distance is same. This is the additional path, right? So that path difference we have denoted by delta x. Observe the diagram carefully. If this angle is theta, according to first approximation, if this angle is theta, then here in this triangle, this angle also will comes to be theta. Then if this angle becomes theta means sin theta is equals to, this distance is delta x, path difference, opposite by hypotenuse, delta x divided by small d. Then delta x is equals to d sin theta. Then what is the path difference? Path difference is d sin theta. So first approximation, if we consider d is very lesser than capital D, or capital D is very large comparing to the distance between two slits, then path difference becomes d sin theta. And next, if x is a second approximation, Okay, if second approximation x is very lesser than capital D, in this case what happens means this theta becomes very small. So see the diagram here again. If x means this distance is small comparing to capital D, that means here arc is decreasing, this length is increasing, then definitely theta becomes small. Then according to second approximation, x is very lesser than D, I can consider theta is very small. If theta is very small, then I can able to say delta x is equals to path difference is d sin theta, that d sin theta is also equal to d tan theta. Theta is small means sin theta nearly equals to tan theta. Then path difference delta x d tan theta means in this triangle, that is d tan theta opposite is x, adjacent is capital D, that is x d divided by capital D. So directly in the derivation, in PU derivation, we came to know that path difference is xd divided by capital D. But when we have to take the path difference as xd divided by capital D, means it has to satisfy two approximation. If it has to satisfy this condition, first condition, then the path difference become d sin theta. Then it satisfies the second condition, then d sin theta I can consider it as d tan theta, then the path difference become xd divided by capital D. While solving problem, we have to observe both the condition. If second condition is not obeying, then path difference is only d sin theta. Two conditions are also obeying, then the path difference is xd divided by capital D. Just as a note, you remember these points. And next, write the heading angular fringe width. Angular fringe width. To understand this concept, let us consider this is a central bright fringe. Bright fringe is also called maxima. Dark fringe is also called minima. And in interference pattern, the width of the bright fringe, dark fringe is same, equal. And intensity is maximum for bright fringe, 0 for dark fringes. So in the Young's double slit experiment, let us say this is a central maxima, CM. And after central maxima, you will get a dark fringe, right? Fringe. Then again you will get bright fringe, isn't it? So this is first bright fringe from central bright fringe, or first maxima from central bright fringe. Then you have mentioned the distance x, isn't it? This distance is x, that is linear position of the bright fringes. X, what it will give? Linear position of the bright or dark fringes. Then this is midpoint. Here this is source 1, this is source 2, this is midpoint, central axis, isn't it? From this point, the first maxima is making an angle theta, angular position, or this is called as angular fringe width. And also you came to know that the consecutive, the distance between consecutive bright or dark fringes, that is nothing but beta. That means this distance is nothing but beta according to the definition. Then what is angular fringe width here? So this angular fringe width, this is the distance capital D from the slits and the screen. So you can see the diagram, this theta is equals to arc by length, means you can write beta by capital D. This is what? Angular fringe width. This equals, beta means lambda capital D divided by small d. Here one more d is there, this d and d will get cancelled. Then the expression becomes lambda divided by small d. Angular fringe width, lambda divided by small d. And also this is useful for a competitive exam. And also the whole apparatus YDSE, Young's double slit experiment, that slits and that source you have take and you take it into the other medium like water medium or any other medium, do the experiments. In that time what happens? So you know that a refractive index mu is inversely proportional to wavelength of light. Then mu1 lambda 1 you can write it as mu2 lambda 2. And mu1, let us consider it as air medium. Air medium refractive index is 1. Lambda 1 is equals to that medium refractive index is let us say mu. So this is lambda 2. Then mu is equals to, or lambda 2 is equals to, this equals lambda 1 by mu. So from this what you came to know, in other medium the wavelength will decreases, and how many times means mu times lambda 1 by mu. The lambda 2 becomes lambda 1 by mu. So the same Young's double slit experiment apparatus you placed in other medium, conduct an experiment. Then what you will observe means, first thing, the fringe width beta is equals to lambda d by d, means beta proportional to lambda. So in other medium lambda decreases to lambda by mu, means in other medium beta will decreases to beta dash, I will consider beta divided by mu. Here theta is directly proportional to beta, right? Then theta dash, that means angular fringe width in other medium, that becomes theta by mu. So remember this formula for competitive exam. That means here lambda 2 wavelength in other medium. This is lambda 1 wavelength in air medium. So wavelength in other medium, lambda 2 is always equals to wavelength in air medium by mu. So it will decreases. Then the fringe width also decreases, angular fringe width also decreases. And next I will explain some problems based on these concepts. So problems based on Young's double slit experiment. First one, Young's double YDSE means Young's double slit experiment is performed with sodium light of wavelength 589.3 nanometer, and interference pattern is obtained on a screen 100 centimeter away. The 10th bright fringe has its center at a distance of 12 millimeter from the central maxima. So here what are the given data means, first given data. So while solving problem in PU exam, in this procedure you have to write, first you have to write given data, that is wavelength lambda 589.3 nanometer 10 to the power minus 9 meters. Interference pattern is obtained on a screen. Slits, the screen is placed at a distance 100 centimeter, right? That is capital D. Capital D value is given 100 centimeter means 1 meter. The 10th bright fringe has its center at a distance of 12 millimeter from the central maxima. Imagine the diagram. So this is a screen, this is source S1 and this is source S2. Then this here at the midpoint which will form means central maximum, bright fringe will form. From this point, what is given? The 10th bright fringe, 1, 2 like that, the 10th bright fringe, the distance is from the midpoint is x, linear position of the 10th bright fringe, that distance is given 12 millimeter from this central maxima. So how to write means x b bright fringe 10th bright fringe distance is given 12 millimeter, 12 into 10 to the power minus 3 meter. Find the separation between the slits. This small d, this is capital D, and this small d distance you have to find. So the formula is, you know that the linear position of the bright or dark fringes. For bright fringes, I will write x b 10, that is equals to n lambda capital D divided by small d. X equals n lambda capital divided by small d, nth bright fringe. In place of n, this is 10th bright fringe. Okay. So here lambda d by d also you can consider beta, n into beta, right? Then in the place of n, what you have to consider means n value you have to take it as 10th bright fringe, 10 lambda d divided by small d, or you can consider xb 10 bright fringe, 10th bright fringe is equals to 10 beta also you can write. Next, substitute the values. So this value is 12 millimeter, 12 into 10 to the power minus 3 is equals to, so here 10 lambda value 589.3 into 10 to the power minus 9, capital D 1 meter, small d value you have to calculate. I will write here. You can write it as D is equals to 589.3 into 10 to the power minus 9. The 10 to the power minus 9, you can write it as 10 to the power minus 8. I removed 110 divided by 12 into 10 to the power minus 3. So D is equals to, calculate this value, finally you will get 0.49 millimeter. This is the value of D. First one. And next problem. In the next problem, these are important for PU exams. In the next problem, two narrow slits emitting light in phase are separated by a distance of 1 centimeter. The wavelength of light 5 into 10 to the power minus 7 meter. The interference pattern is observed at a distance of 1 meter. These are the two narrow slits, light emitting in phase, separated. These two slits separated by distance 1 centimeter. The wavelength of light used, the wavelength, that is lambda, is equals to 5 into 10 to the power minus 7 meters. Okay, lambda value is given. Lambda is 5 into 10 to the power minus 7 meters. D value, separation between two slits, is given 1 centimeter, 1 into 10 to the power minus 2 meter. Find the, and it is observed, there is a screen. On the screen, this interference pattern is observed, that the D distance is 1 meter. Capital D is equals to 1 meter. You have to find the separation between two maximas. The separation between two maximas is nothing but fringe width. Consecutive distance, the distance between consecutive maxima, that is the meaning. You have to find the beta value. That is the first question. Second question, find the separation between slits, which will give the separation for separation of 1 millimeter between two consecutive maxima. First I will find the first one. Beta equals lambda capital D divided by small d, then lambda 5 into 10 to the power minus 7 into capital D is 1 meter, and d, small d is 1 centimeter, 10 to the power minus 2 meters. This is the small d value. Then beta value, here you will get 5 into 10 to the power minus 5 meters. This is the fringe width, the separation between two maximas. Then after calculating that value, the second question, what is asking, slits separation, d value you have to find, separation between the slits, which will give separation of 1 millimeter. Beta dash I will consider for second question, that separation is 1 millimeter. Separation of 1 millimeter between two consecutive maximas, nothing but beta, separation is 1 millimeter. So for the same given data, beta dash value is given. So beta dash is equals to lambda capital D divided by small d. So beta dash value is given as 1 millimeter, 1 into 10 to the power minus 3 is equals to lambda. Lambda is 5 into 10 to the power minus 7, and capital D is 1 meter divided by small d. Small d value you have to calculate. Again, small d value, it will comes to 5 into minus 10 to the power minus 4 meter. Right, 5 into 10 to the power minus 4 meter, or this small d you can write it as 0.5 millimeter. This is the separation between two slits. And next problem, in Young's double slit experiment, the slits are separated by small d value. Small d value is 0.28 millimeter, 10 to the power minus 3. The screen is placed 1.4 meter, capital D 1.4 meter away, the distance between central bright fringe and fourth bright fringe. So again, this is the screen, means this is central bright fringe, central maxima. From this first, second, third, fourth maxima, fourth bright fringe. This distance is given, it is denoted by x. That distance is given 1.2 centimeter. Determine the wavelength of light used. Then this x B3, fourth bright fringe, right? So that value is given how much? 1.2 centimeter into 10 to the power minus 2 meters. Lambda value you have to find, xb4. xb4 is equals to n lambda capital D divided by small d. So here this value is 1.2 into 10 to the power minus 4. This equals n value is 4. You have to consider fourth bright fringe is given into lambda value you have to find, capital D 1.4 meters divided by small d, that is 0.28 into 10 to the power minus 3. Then lambda value you have to find, that is I will write here 12 into 10 to the power minus 4, that becomes 1.2 means 12 into 10 to the power minus 5. This equals 4 into lambda into 14 into 10 to the power minus 1 divided by 28 into 10 to the power minus 3. Then here 1 times, here 7 times, again 1 time, here 2 times. Then finally on this side you will get 6 into 10 to the power minus 2 ones are here 6 into 10 to the power minus 5 is equals to lambda 2 divided by 10 to the power minus 1. If If this 10 to the power minus 1 comes to denominator, means plus 1 minus 2. So here overall you will get 6 into 10 to the, you calculate 6 into 10 to the power minus 7 meters. Okay, this is the value of lambda, or you can consider lambda is equals to 600 nanometer. This is the wavelength of light used. And next, fourth one, a beam of light consists of two wavelengths, 650 nanometer and 520 nanometer. Up to now we are using a single wavelength, right, monochromatic light. In this problem, two wavelengths, one is 650 and another one is 520. Is obtain interference fringes in Young's double slit experiment. Find the distance of third bright fringe on the screen from the central maxima for wavelength 650 nanometer. So first, for A question, always we are finding bright fringe only. Dark fringe means just one more formula is there, no. X n b, you can x and d you can write dark fringe, nth dark fringe 2n minus 1 lambda d divided by 2d. In this formula you can able to calculate the dark fringe also. In next classes I will give some problems based on that dark fringes. So here A, find the distance of third bright fringe on the screen from the central maxima. X 3b is equals to n lambda d divided by capital D. I hope pause the screen, solve the problem. X here, x3b is equals to n value is 3, lambda 650 nanometer, 650 into 10 to the power minus 9 into capital D. Capital D value is not given, in terms of D only you write divided by small d. Then small d value is also not mentioned. So final answer we will get in terms of capital D and small d only. That is x3b is equals to here how much you will get, 650 into 3, that is 1950 into 10 to the power minus 9 capital D by small d. This is the answer. Bright fringe distance from the central maxima for wavelength 650 nanometer. And next question, you observe what is the least distance from the central maxima where the bright fringes due to both the wavelengths coincide. That means on the screen only one wavelength we have used, that will form a bright and dark fringes. Two wavelengths means that two wavelengths also will form their separate fringes. For 650 nanometer is one fringe and 520 nanometer is another fringe. You know that beta is directly proportional to lambda. If lambda wavelength is more means fringe width is also more. That means 650 nanometer fringe width is more. 520 nanometer fringe width is less. Right. Then in that case, how to understand this concept means, let us consider these are the fringes. Fringe width of 4 millimeter of first wavelength lambda 1. Lambda 1 is greater than lambda 2, let us take. And another wavelength, it is a lesser wavelength, right? Comparing to first, its fringe width comes to be 3 millimeter. What this 4 millimeter coincides 3 millimeter? No. Second fringe 4 millimeter. This second fringe 3 millimeter. So total is 6 millimeter, 8 millimeter. Next, third fringe. Here also this third fringe Okay, here 9 millimeter, here 12 millimeter. Now also not coinciding. Next, fourth fringe 16 millimeter, and here fourth fringe, okay, 12 millimeter. Now you can observe, okay, here this 3 fringes, here 4 fringes, 12 millimeter, right? For 12 millimeter, here also 3 fringes. That means here wavelength is more. So how many fringes you are observing? 1, 2, 3. So total distance is 12 millimeter. So to have the 12 millimeter, here how many fringes is required? 1, 2, 3, 4. That means 4 fringes of second wavelength is coinciding the 3 fringes of first wavelength. I hope you understood. Like this. This is the minimum distance. Then after again, like that you go on continue. Again, once again they will coincide after some distance. But least distance means this distance we have to find in the problem. For that direct formula you apply, that is n1 lambda 1 is equals to n2 lambda 2. Or you consider for the first fringe, that distance, x distance is, bright fringes is mentioned, right? Bright fringes. X n b is equals to x n dash, here bright fringe. This is for first wavelength. This equation for second wavelength. Then this in this wavelength you can see how can I write n lambda capital D. This is lambda 1, let us take lambda 1 capital D divided by small d. This should be equal to coincides. Both distance should be same. N lambda 1 capital D divided by small d, n lambda 2 capital D divided by small d. So here d and d get cancels, right? So then I can able to write it as n1 lambda 1 is equals to n2 lambda 2. Then n1 by n2, you observe carefully that will come lambda 2. Lambda 2 is 520 by lambda 1. Lambda 1 is 650. Then here you will get the answer 4 by 5. This is 4, 13 4s are 13 5s are, isn't it? N1 by N2 value you got it as 4 divided by 5. Then substitute these values in any one expression. That is N1, here N1, this is N2, N1 lambda 1 capital D divided by small d. If I take this expression, so in the place of N1 I have to substitute N1 value 4 lambda 1. Lambda 1 is how much? 650. 4 into 650. 4 into 650 multiplied by d divided by small d. 650 nanometer, 10 to the power minus 9 capital D divided by small d. So this is the answer. So at what distance you will get? That means I will consider xnb. Xnb is equals to how much you will get here? 650 into 4, that is 0, and here 2, 2600 into 10 to the power minus 9 capital D divided by small d meters. At this distance the fringes, bright fringes will coincide.